Okay, here we go. We are doing a quick tutorial over 5.1 and 5.2 trig verifications and simplifications. Hope you enjoyed this little comic strip I found. All right, so what do we need to be able to do our verifications? We need to have our identities memorized, and we need to be able to um, be proficient on all of our algebra skills. And so we're going to find that it's much easier to memorize the identities than it is to sharpen our algebra skills. One requires just a willingness to memorize, and the other requires a willingness to make mistakes and learn from them. So what else is needed? Well, when we're asked to do trig identities, well, we're asked to do trig verifications, they look like this. We'll have some trig stuff on one side, an equal sign, and some trig stuff on the other. So before we do the trig stuff, let's talk about what we are doing conceptually. Normally when we see something with an equal sign, when we see an equation, we know we're solving it. But with verifications, we are not solving. With verifications, we simply want to make one side look like the other. And so we're going to draw a line down where our equal sign is, and we want to make the left side look like the right. Now this is much more understandable when we use algebra, so that's why I'm doing it this way. So we think, okay, well, what are we going to do first on the left side? We're going to distribute. So we'll distribute that 5. We're not writing anything on the right. And then what else can we do? We can gather like terms. 5x plus 3x is 8x, and 12 minus 20 plus 10. Let's see, that's going to be minus 10 plus 12. That's going to be a plus 2. Well, look at that. We made the left side look like the right side, and we're done. That's what a verification is, making the two sides look the same. So once again, we need to have our trig identities memorized. We need to be pretty proficient on our algebra skills, and we need to have a willingness to try different strategies. So here's our first example. We want cosine theta times the quantity tan theta plus cotan theta to equal cosecant theta. So as a reminder that I am not in an equation, I'm going to put a line down here. And here we go. I'm going to think about some of the things I could do. And the first thing that just pops out at me is I can distribute. So I'm going to go ahead and distribute cosine theta times tan theta. Well, that is simply cosine theta, tan theta. And then when we have cosine theta times cotan theta, it is also cosine theta, cotan theta. Once again, I'm not going to write anything on the right. And so I look at this and nothing pops out at me. So when a strategy isn't readily available, I can choose to use my identities and turn everything into sines and cosines. So cosine obviously already is in terms of cosine and sine. So tan theta, I remember with my identities, that's a sine theta over cosine theta. So I use my identity and I substitute in. Instead of rewriting tan theta, I use the fact that tan theta equals sine theta over cosine theta, and I substitute it in. Then I bring down the plus. Cosine is fine the way it is, and I think about cotan theta. Cotan theta equals cosine over sine. So because they are equivalent values, I'm going to plug that in. I'm going to substitute it in. So once I do that, then I'm going to do some simplification. Cosine theta over cosine theta, that cancels out. So I'm left with a sine theta plus, then I have, unfortunately nothing cancels out here, but when I think about what they're asking me to do, it might be easier to see if I put cosine theta over 1. Now we can see it's a fraction times a fraction. So cosine theta times cosine theta is going to be cosine squared theta. And then 1 times sine is sine theta. It's getting long, but we're getting closer, I promise. So here we go. Now I notice that I've got a fraction plus a non-fraction. And so I need to create sine theta as a fraction so I can add it to cosine. squared theta over sine theta. So the first thing I'm going to do is make it look like a fraction. The second thing I'm going to do is decide on the fact that I need both of my fractions to have the same denominator, because I cannot add fractions unless they have the same denominator. So since my second fraction has a denominator of sine theta, then I'm going to make this first one have the denominator of sine theta as well. So that means that to make this sine theta, I had to multiply my denominator times sine theta. Well, I'm not allowed to do that unless I do the same exact thing to the numerator. Can you see how sine theta over sine theta is just 1? I'm allowed to multiply anything times 1, and I'll still retain the value of my original term. So sine theta times 1 is sine theta times sine theta is sine squared theta. And then, because I didn't have to do anything to the second fraction, I leave it like this. And now I'm like, great, I've got two fractions. They both have the same denominator. So now I'm going to combine them. And we need to remember, when we combine fractions, we keep the denominator the same, and we add the numerator. Now, if you know your identities already, you see where we're going. Because I know that sine squared theta plus cosine squared theta equals 1. That is one of my identities. And so instead of writing sine squared theta plus cosine squared theta, I'm going to substitute in 1. If that confuses you, just remember, I'm going to write this as if I'm writing it on my margin. One of my identities is sine squared theta plus cosine squared theta equals 1. If you knew that already, then you got the joke that was on the first slide. If not, you may want to go back. All right, so because there's an equal sign here, that means that sine squared theta plus cosine squared theta is an equivalent value to 1, and I can substitute in 1 whenever I see sine squared theta plus cosine squared theta. And I'm almost there. What is 1 over sine theta? It is cosecant theta. Let's go back to the top of the problem. There we go. We've got cosecant theta. So we bring it down, and we've got cosecant theta equals cosecant theta. So once again, let's look back at this problem that we just did. The big mess actually does turn out to be equal to cosecant theta, and we used distributive property. Then we simplified. Then we used distributive property. Then we used the identity of tan equals sine over cosine and cotan equaling cosine over sine. Then we used simplifying. Then we used combining two fractions by finding common denominator. And then we used the Pythagorean identity. And then we used the fact that 1 over sine theta is equal to cosecant theta. So lots of identities and some algebra. All right, with the second one, it's pretty obvious to me the only thing we can do right now is to distribute. A lot of people learn this in 8th grade as foiling. I prefer to think of it as distributing, because then you can distribute. You can do any problem no matter how many terms are in that problem. So secant theta times secant theta is secant squared theta. Secant theta times tan theta is just simply secant theta tan theta. And now it's time to distribute the negative tan theta. Negative tan theta times secant theta is minus tan theta secant theta. And negative tan theta times tan theta is, minus tan squared theta. Okay, once again, I should have started this problem by putting a line down here, because I'm just going to work one side. So when I look at it, it becomes obvious that I have two terms I can combine. I've got secant theta tan theta minus tan theta secant theta, which is the same thing. So those two cancel out, and I am left with secant squared theta minus tan squared theta, which reminds me of secant. So in the column, this is not part of my proof, but in the column, if you want to remind yourself of the identity, it is secant squared theta equals 1 plus tan squared theta. And so because the equal sign means that what's on either side is equivalent to the other side, then I'm going to use substitution. When I see secant squared theta, I'm going to substitute in 1 plus tan squared theta. And then I'm going to rewrite what's left, minus tan squared theta. You know what, let me do that in a different color so that you can see all I did was substitute in, when I saw secant squared theta, I used my identity and I substituted in an equivalent value. So now I look at it, it's like, oh, this is great. I can combine like terms. I see that I have a positive tan squared theta and I have a minus tan squared theta, which goes away. I'm left with my 1. And that, my dear students, 1 equals 1. I am done with my verification. This one was a lot quicker than the other one. Sometimes they're fast, sometimes they're slow. All right, notice that with each verification that we do, we're gaining new practice. This one, the new practice was distributing a binomial to another binomial. And then, of course, using the identities is something we need to always get used to. We also combine like terms, so we're doing a lot of algebra in these verifications. All right, here it's pretty obvious. I'm given 2 fractions that I want to combine the 2 fractions together. And I cannot combine 2 fractions together until I have a common denominator. So hopefully you can see that our common denominator needs to involve both the cosine theta and the 1 minus sine theta. So for both fractions, we're going to have the same denominator. And we're going to remind ourselves that we are in a verification, so we're just going to work the left side until it is equal to the right side. All right, so let's talk about how we did this. Our first fraction, the original denominator, which is cosine theta, but I went ahead and changed it by multiplying the denominator by 1 minus sine theta. I'm not allowed to do that unless I also do it to the numerator, because as you can see, if I do that, then it's just multiplying the fraction times 1 in disguise, and that is legal. So here we go. Let's multiply. 1 times 1 is 1. 1 times negative sine theta is negative sine theta. Negative sine theta times 1 is negative sine theta. And negative sine theta times negative sine theta is a positive sine squared theta there. I just squished it on. Okay, same thing with this fraction over here. I already had the 1 minus sine theta as part of my denominator, but I did not have the cosine theta, which means that I multiplied the denominator by cosine theta, and to keep the value, the original value, the integrity of the original value of this term, I have to also multiply the numerator by cosine theta. So cosine theta times cosine theta is cosine squared theta. And there we go. We just rewrote these original 2. Let's see if we can find these original 2 fractions are now written. They look totally different, but they are the same fractions that we started out with. They look different, but they have the same value as the original ones. So now we've got 2 fractions, and we're going to combine them by adding them together. And so let's see, let me switch up a color. Our next step is, once again, when we add fractions, our denominator stays the same. And we go ahead and add the values in our numerator. First of all, we can see here that negative sine theta minus sine theta, I can combine those. You know what, I should probably have, I'm kind of skipping a step here, but forgive me. So I see that this is, I'm going to bring down the 1. Negative sine theta minus sine theta is negative 2 sine theta. And then I've got the plus sine squared theta. And then I'm going to bring down the positive cosine squared theta. All right, so I combined the numerators of the 2 fractions. I also combined the 2 common terms up there in the first fraction. All right, so let's see what we've got. Wow, we can see how it's going to work itself out. The first thing I notice is that I've got sine squared theta plus cosine squared theta. And we know what that's equal to. It's equal to 1. So that's going to be my next step. I'm going to rewrite everything else except for, instead of writing sine squared theta plus cosine squared theta, I'm going to substitute in 1 because 1 is equivalent to sine squared theta plus cosine squared theta. And I know that because I memorized my identities a long time ago, like back in the 80s, probably a little in the 70s too. All right, so here we go. My denominator is the same. And now look at this. We had a lot of fun in class going. We never thought we would be saying this in pre-calc, but 1 plus 1 is 2. We had some fun with that in class. 1 plus 1 is 2. I'm going to rewrite everything else, and hopefully you're getting to see where this is going. I told you guys in class that I've learned from all my years of doing verifications that whenever I have a denominator in factored form like I have now, I don't go ahead and distribute it because there's always a payoff for keeping it in factored form. And this case is no different than most other cases. So I see this 1 minus sine theta. And I'm like, this is looking kind of like 2 minus 2 sine theta. And so I think about what do I need to do to make my numerator look like my denominator. And so I think about the GCF. This is a term, 2, and my other term is 2 sine theta. What's in common? A 2. So I get to factor out a 2, and I ask myself, what's left? If I factor out a 2 from 2, it's basically saying if I divide 2 by 2, what's left? 1. I bring down the minus. If I divide 2 sine theta by 2, what's left? Sine theta. Some people really have difficulties in factoring out the GCF, but you can always check yourself to make sure you do it right, because think about it, if you do the distributive property, you get back to where you started. I'm going to undo that. There we go. All right, so I rewrote the numerator by factoring out the GCF, and then I'm going to just rewrite the denominator, and I'm going to notice something. Now, this is really important. I'm not allowed to cancel out any term that's combined by addition or subtraction. So I want you to understand I'm not doing that. See the 2 and the 1 minus sine theta on the top? There's a multiplication there. Okay, so same thing with the cosine theta and the 1 minus sine theta, there's a multiplication there. Okay, so I'm allowed to take out something I'm taking out the whole 1 minus sine theta and canceling out with the 1 minus sine theta on the bottom. Okay, I'm allowed to do that. And what's left is 2 over cosine theta. And then we ask ourselves, well, what's 1 over cosine theta? 1 over cosine theta is secant theta. So if we have 2 over cosine theta, that is 2 secant theta. And let's hope that that's what we started with on the right side. Oh my goodness. Yep, 2 secant theta. So we say equals to 2 secant theta. And yes, we put the check mark to say we just verified it. Once again, verifications, like proofs, are for the reader. So you want to make sure that you don't skip steps so that the reader of the verification understands that you really did verify that one side equals the other. And so in the case of your test, I am the reader. So make sure you show all of your steps. Okay, now the next 3 examples we're just simplifying. So note our verifications had equal signs. When we were asked to verify, we always had an equal sign. When we're asked to simplify, there's no goal in mind. There's nothing on the right side. There's just a term, and we're asked to simplify it. So here we go. In class, we noticed that we had the difference of 2 squares. This is a perfect square. this is a perfect square, and this minus means difference. And we can remind ourselves, if we had, once again, this is like our scratch pad, this outside part, if we had x squared minus 4, we would know how to factor that. It's the difference of two squares, so we'd have x plus 2 and x minus 2. Well, it's the same thing here. We can rewrite this as cosine theta minus 2 and cosine theta plus 2. It doesn't matter if you write the minus or the plus first. And that we get a payoff right away because we can cancel out this whole cosine theta minus 2 with the cosine theta minus 2, and we end up with cosine theta plus 2. There's nothing to check with it on the right side. We just have to ask ourselves, can we simplify this any further? And the answer is no, we can't. This is our most simplified form. So these simplifying ones, actually, the more we do of them, it's going to help us to become experts at verifications. So who doesn't want to be an expert at verifications? All right, so example 5, this looks a little tricky until we notice that it's not in standard form. When we see anything with exponents, we like to have them in descending order. It just helps us to make more sense of what we're looking at. So that's a strategy there, right? To get the exponents in descending order, we'll have to add that to our list. And so this reminds me of some Algebra 2 topics where we would have, once again, this is just my scratch pad. It's not really part of my problem, but it's to remind me of some different strategies. I'm going to check our time. Okay, so it's going to remind me of some different strategies. And so if I had x to the 4th, I'm not sure why I'm writing it in parentheses. All right, if I had x to the 4th plus 2x squared plus 1, note what I did. I'm looking at what I have, and instead of doing the tans, instead of the function being tan, my function is just, you know, y equals x to the 4th. I know that I can factor it out. In fact, it's the perfect square trinomial, right? If I distribute, I'm going to get x to the 4th plus 2x squared plus 1. So that gives me a clue about what to do with this. I can factor this out as tan squared x plus 1 and tan squared x plus 1. If you don't believe that these two things are equivalent, please pause the video and take your time to distribute, and you'll see that you get right back to where we started. And then this is very exciting because I know my identities, and secant, that goes together. So I have to remind myself secant squared theta, or secant squared x, equals tan squared x plus 1. So I'm going to use substitution. The equal sign says what's on this side is equivalent to what's on that side. So when I see tan squared x plus 1, I'm going to substitute in secant squared x, and I'm going to do that twice. And then we have to remind ourselves real quickly that if I had, this is a different color, if I had x squared times x squared, then I add my exponents, and I'd have x to the 4th. Same thing here. I will have secant to the 4th power of x. So that's as far as I can simplify it. I cannot simplify it further. And our last, oh, is that it? I only have 2, right, it says 4 through 6. Let's see. All right, we're done. So I want you to notice that the homework here does not, yeah, I think it does match what you have on your paper. It does not match what's on the pacing guide. I believe there are more problems right here, and I do not want you doing them. The problems that are on page 345, I forget which numbers they are, do not do. And the other thing is we can get rid of the vocab check. We don't need that. All right, thanks for joining me, and I look forward to seeing you in class.